The entire AI revolution, it really runs on these tiny chips of almost unimaginable complexity. So today, we're going to go on a microscopic journey to see how these things are actually built, layer by painstaking layer. And it all kicks off with a really simple question.
Right? Why build up instead of out? Well, it's for the exact same reason we build skyscrapers in crowded cities. You eventually just run out of space. To cram more power and speed into a chip without making it huge and slow, engineers had to start thinking vertically. And honestly, this one idea changes absolutely everything.
And that brings us to this stuff, high bandwidth memory or HBM. It's a genius solution. Instead of laying memory chips out flat, side by side, you stack them right on top of each other. This creates this super fast, incredibly wide highway for data to move around, which is exactly what modern AI needs. But how in the world do you connect all those stacked layers? Well, the answer is a truly incredible piece of engineering called the Through Silicon Via, or TSV. The best way to think of it is as an elevator for data. It just shoots information straight up and down through all the different floors of our memory skyscraper. This little piece of tech is the key that makes the whole thing work. So our journey begins right here, because before you can even think about building the skyscraper, you have to install the elevators. This first part is all about creating those vertical data highways, the TSVs, that are going to connect every single floor. The whole process is kind of like a three-step dance of microscopic precision. First step is etching, which is basically drilling these super deep, narrow trenches into the silicon wafer. Next, you have the fill, where those trenches get packed perfectly with conductive copper. And finally, the whole surface gets polished completely flat, so all you have left are these perfect little columns of our data elevators. But that second step, the copper fill, let me tell you, that is a massive challenge. I mean, these trenches are incredibly deep compared to how wide they are. And the absolute non-negotiable rule is that they have to be filled completely. No air bubbles, no voids. Just one tiny empty space could break the connection and poof, the whole chip is useless. The level of precision needed is it's mind-boggling. All right, so with our data elevators installed, it's time to get the individual floors ready. Each one of these silicon wafers has to be prepped for stacking, and every single connection has to be absolutely perfect. Now, the first thing they do here is make the wafer incredibly thin using a process called back grinding. And yeah, this obviously helps make the final stack smaller, but the other benefits are maybe even more important. It gets rid of any contaminated layers, it actually lowers power consumption, and this is critical, it helps heat escape, which is a huge, huge problem when you're packing this much power into such a tiny space. Okay, but this creates a brand new, very real problem. Once you grind a silicon wafer down this thin, it becomes extremely fragile. We're talking potato chip fragile. So how do you keep working on it, polishing it, adding connections, without it just shattering into a million pieces? And the solution is just so clever, it really shows you the genius behind this process. What engineers do is bond a temporary carrier wafer to the front. This thing is sturdy and it acts as both a handle and a shield, letting them do all the delicate work on the back of that thinned wafer without it breaking. So with the wafer all stable, it's time to add the connection points. And this is key. For a stack to work, every chip has to connect both up and down. So on the front side, they form these little connection points called bumps. Then on the back, they expose the tops of our TSV elevators and create another set of bumps there too. Okay. The elevators are in, the floors are prepped, the connection points are all ready to go. Now for the most exciting part, assembling the skyscraper. This is where all those individual layers finally come together to form one single incredibly powerful HBM chip. So how do you glue these ultra-thin layers together? As you can see here, the methods have really evolved. Early techniques like mass reflow were kind of like baking the whole stack. It worked, but it was risky. It could actually warp the thin chips. Then you have thermal compression, which is more like a targeted hot press, much more precise, but also a lot slower. The real cutting edge now is laser-assisted bonding. It's incredibly fast and gentle because it heats only the joint, leaving the rest of the chip cool. So you can see each method is a trade-off between speed, precision, and the stress you put on the parts. But one of the most innovative methods out there, used by industry leaders like SK Hynix, is called MR-MUF. It's sort of a hybrid approach. It uses a lower temperature reflow, and then, in one single step, it fills all the tiny gaps between the chips with a protective material. This makes the whole process fast, super reliable, and it's perfect for protecting these delicate stacked structures. And with that, the assembly is complete. All of those complex, microscopic steps have finally come together. And what we're left with isn't just a chip, it's a marvel of three-dimensional engineering that is literally going to power the future of computing.
To really, truly grasp the scale of what's happening here, just look at this number. Every single layer in an HBM stack needs at least 1,024 microscopic bumps to be perfectly aligned and bonded to the layer below it. That's over 1,000 perfect connections, each one smaller than a grain of pollen, repeated for every single layer. It's just incredible.
You know, this entire journey really boils down to this one idea. We've watched a simple blank canvas get transformed into a multi-layered skyscraper of high-performance memory. A flat piece of silicon has become an absolute powerhouse, ready for the most demanding AI jobs you can possibly imagine. This vertical stacking of HBM is what makes today's artificial intelligence possible. It's a true testament to unbelievable engineering and just relentless innovation. And that leaves us with one final thought. If this is the crazy, complex process we need for today's technology, what new marvels of manufacturing are we going to need to build the AI of tomorrow?